You're listening to the Turing Podcast, a production of the Alan Turing Institute, the UK's National Institute for Data Science and Artificial Intelligence.
Hello everyone and welcome to another episode of the Turing Podcast. I'm your co-host Ed Cowstreet and I'm here with B. Costa Gomez. Hi B.
Hi Ed, how are you today?
I'm doing good. We're still in partial lockdown. It's 27th of May we're recording this episode. How are you doing up in Manchester?
The weather is so nice. I am so confused as to why is it such a nice weather, but I'm enjoying it. Just going to the balcony and probably will get sunburned.
It seems that the weather's been unseasonably good throughout lockdown. I'm not sure why that is.
I think it was on purpose. The weather decided to just make us all feel...
Just to troll us, yeah.
Yes, exactly.
That bit works,
gigantic nature troll on us. That's what's happening.
So, B, we've got an interesting guest today, Eric Daub. I'll introduce him in a moment. But before we do that, we've got a couple of fun facts. And my facts today are very relevant to the today's episode. They are bridge-related facts. Would you like to hear them?
Oh my God, you have bridge-related facts. Yes, I would.
Well, in fact, I'm going to ask you them as questions to see if you get the answer right. So here we go.
Oh God, I'm not prepared for this. I did not agree with this, with being quizzed, but
you're gonna be really embarrassed if your answer is way out. But here we go. The world's longest bridge is the Danyang Kunshan Bridge, Grand Bridge in China, which is part of the Beijing-Shanghai high-speed railway. Can you guess how long it is in kilometers?
No, I have no idea.
It's 165 kilometers.
Oh my God, I would have been way off. I was going to say 10, but that's like so much more.
One order of magnitude out. It's a little bit longer than the bridge we'll be discussing today with Eric.
Slightly longer.
I know, slightly longer, yeah. Related question. The bridge with the tallest structural height is the Malau Viaduct in France. Can you guess how tall that is?
Oh God, no. I can't
Go on,
guess
have
it.
a go at this one.
Okay. So I guess it's going to be like I don't want to do this because I more than, I don't know, 100 meters. Is that it?
You're in the right ballpark, but it's a fair bit taller than that. It's 336 meters.
Okay, it's more than 100 meters, so I'm technically correct. So
you got it right. Well done. Correct. So those are my fun facts / fun bridge-related questions.
I don't have a bridge related fact to you, but I can tell you a fact that I learned a couple of days ago. Did you know that there are more plastic flamingos in the world than actual flamingos? More
plastic flamingos than actual flamingos? And who's measured that exactly? Who's found this?
I have no idea, but it's just imagine that the flamingos
is this one
are
of those
being taken
facts
over.
like you swallow 8 spiders a night? Is that kind of fact?
I don't know. I hope not. But I'm just imagining there's like an army of real flamingos very upset that there are more plastic flamingos than actual flamingos. So
I know that there's more Lego people than real people in the world. So okay,
that's a good one though. That's Is it? Did they count all of the Lego people in the world?
Yeah, no, that's another one. How did they count that? Who's counted that? I don't know.
Someone's job is to count that.
It's gone around.
Just think about it. Also, someone's job is to test chocolate. That was my dream job as a kid. So just that. Someone's
got that job, yeah. Someone's got the job to count flamingos.
Yes. But tell us more about who are we going to talk to today?
Yes, let's do that. Today we're talking with Dr. Eric Daub, a principal research data scientist at the Alan Turing Institute, whose prior research has involved using computer simulations to understand the complex dynamics of earthquakes and material failure, But today we're talking to him about his involvement in measuring, monitoring and analysing the performance of the world's largest 3D printed metal structure, a 12-metre long stainless steel bridge, which will be crossing one of Amsterdam's canals, although as we found out, it's not currently crossing the canal. Eric, welcome to the podcast.
Thanks for having me. It's a pleasure to be here.
So I'll kick off by just asking you a question about this bridge then. So this 3D printed bridge, it has an accompanying software model that's been called a digital twin. Well, let's start with that actually. So what's a digital twin? And what's the motivation behind their development?
So digital twins are a big push within the Turing in terms of a general idea about how to understand, the built world around us. I think, it also has applications beyond engineering, but for the bridge, this is kind of its flagship implementation in that we have a real physical structure and then we have a computational digital model of that. And we'd like to learn about the real thing using the computational model. And then we'd like to use data from the real structure to improve our model so that we can, better understand how to construct these things and to accurately learn things about uncertainties in our world. So go ahead.
So these are all about improving real world engineering things by having super accurate computer models, but essentially the key sort of novel component compared to a usual computer model is that it's getting input data from the actual structure.
Yeah, so the feedback is a really important part of this because in traditional engineering practice, you would run your model to make some design specification and then build your bridge and then not really ask yourself if your model was any good. Like just because the bridge doesn't fall down doesn't mean that you did a good job engineering it. You could have over-engineered it, you could have wasted money, you could have, done something completely wrong. And just because the bridge doesn't fall down doesn't mean you did a good job because you don't actually have data that confirms that what your model said should happen is actually what happened. So this is part of an effort to actually bring a rigorous data-intensive approach to engineering so that you can actually, in real time, hopefully over, I think that is one of the goals of this bridge project long-term is to actually try and do this on real time, or at least sort of like a daily update. Like you have some sensor information from the bridge, you feed that into your model, you run some kind of update and you say, okay, like that's exactly what I expected it to do, given that I think my model's really good. Or, there's a problem here, I think I can improve my model in this way. Or or you can even feed back the other way and say, that's a really anomalous occurrence based on everything we've seen before. That should tell me I should be worried about the structure. There's something that's not performing the way that you like. So I think part of that really is the feedback is actually getting real data in real structures to tell us if engineers are doing a good job in their models or not.
How sort of new of an idea is this? Obviously, we're promoting it and doing projects involving it at the Turing, but how widely adopted is it as a practice already?
So just for a scale, we have 100 sensors, give or take, on this bridge, recording continuously at roughly 100 hertz. So my background in earthquakes, that's a place where there's a lot of continuous monitoring going on. A seismic network of 100 would be gigantic. Usually we might be lucky if we have 20 or even 5 sensors in a particular place. To pack that all into a 12-meter structure gives you some really high fidelity information that hadn't been available before, just because there wasn't the bandwidth to sort of transport that. You need cloud computing infrastructure.
Right.
So there's some server physically located at the bridge that's continuously monitoring all these sensors, taking that data, collecting it, sending it to the cloud. So, and then in the cloud, you might have some virtual machine somewhere. That's where that data is stored. Then you bring your model into that and you do some computations and you try and actually dictate what's going on with the bridge. Doing that in that sort of time scale is not really something that's been feasible before or at that level of the number of sensors. So both the real-timeness and the density of sensors are really novel on this. Like I used to live in Memphis, Tennessee, and there's a bridge spanning the Mississippi River there, and that has 3 sensors on it, and that's a really important physical asset. And that's a real pain to sort of monitor and update. The seismologists I work with were actually in charge of that because it has so much parallels with seismic monitoring rather than actual engineering. So, engineers are much more go stick a sensor on something, wait a few hours, and then take it off, not doing this continuous approach. That's sort of the new thing that we're trying to incorporate in this project.
It makes sense that with your background in studying earthquakes, that would be a similar kind of approach you're taking in this case.
Yeah, definitely. My PhD was in computational physics, but I was very interested in how to apply numerical models to really complicated systems. And the bridge is a great example of that. There's little pieces of that that are funny shapes, and so you need a really good computational model to be able to try to predict things on that, much more so than kind of traditional engineering approaches where you kind of put a few sensors on there or you jump on it and that's that. We're trying to do something much more sophisticated with like laser scans. We have really clear picture of what the shape of the structure is like. We've tested these materials at lots of different scales, from like little 2 centimeter.
How does the laser scan work?
So the laser scan, basically you place your laser and it uses the laser, it shines light off of that and measures the amount of time that it takes the light to go back and forth from your position. And so it can actually get a very detailed map of the height of the surface over sort of by doing a scan. I'm drawing in the air what sort of the laser scan would be doing. But
so these are the kinds of so the laser scanning is the kind of sensor that's placed, or one of the kinds of sensors that placed on this bridge across the Amsterdam Canal.
So there's kind of 2 different scales of measurements that we're doing. So one is sort of in controlled environments. So these are things like the laser scan to get a clear, detailed picture of what the actual structure looks like. Then there's like controlled tests in the lab where we put certain demands on it. We say we get 20 people to stand on the bridge and have them jump up and down and record those. And so that's kind of like controlled tests. But in the real bridge, we're going to have completely uncontrolled environment. It's just going to be responding to people walking on there. So we're going to have several types of sensors, including accelerometers that measure small vibrations, to strain meter.
So sorry, Eric, just explain there. When you say the real bridge, so what do you mean there?
Yes. So the bridge is real right now, but it's currently not installed in Amsterdam. And so we're going through the final engineering testing to ensure that the structure is safe. I think because there's no structure like this in the world, we're being fairly conservative in our testing to be sure that we're confident in the safety of this structure. So that's sort of like one extreme. But
I know that there was a miniature version of it, right? So is that the only one that's sort of been plugged into the digital twin, as it were, so far?
Yes and no. So we do have sensors from the sensor recordings from the 12-meter version of the bridge. There's a 2-meter version of the bridge that the Turing has. And in our initial testing, we worked out some hardware and software components to detect when people were on the bridge, how they were moving based on the sensor readouts. And that was meant to be sort of a pilot project for this, to understand some of the challenges in detecting what people were doing on the bridge. But that bridge only had 3 motion sensors on it, plus 4 sensors measuring the weight on the bridge, while the 12-meter version is going to have many, many more sensors that measure the vibrations of people walking on the bridge.
Why Amsterdam, though? Is there any reasoning as to where the real bridge is going to be?
So the company that is printed the bridge is called MX3D, and they're based in Amsterdam. So I think that was a big part of motivation, was just that they wanted to be, tied to their community. They really think of this bridge as a living laboratory for learning about engineering, about new materials, about how people socially respond to new types of construction, new types of things being digital that we didn't, Internet of things that we didn't think of as being digital before, now all of a sudden having some digital component to it.
Right. Yeah. It's like, I guess in this sense, it's you said the Internet of Things. That's sort of a buzz phrase, as it were.
Yeah.
And then the other one that came to mind was smart city, and I guess digital twin fits quite nicely into that.
No, absolutely.
A group of buzz phrases as well. You kind of already answered another question I had, but so when this project was initially being thought up, was the main aim to be a proof of concept for the idea of digital twins, or was it more focused on the novel material of the 3D printed bridge, which was the main thing you wanted to test out, or is it both?
Definitely both. I think that part of the motivation was this being a new material that people didn't understand as well. I think gives rise to the desire to really meticulously instrument and test out how this structure is performing. And I also think that kind of what's neat about the 3D printing is it gives you freedom of design that you didn't have before. So there's only certain shapes that's easy for a machine to roll steel into. Well, if you're just printing it one layer at a time, you can have, and if you see the bridge, it's kind of got these swooping, curvy structure to it that is not like what you would think of being a traditional bridge. And so because of the new material, that kind of motivates that desire to want to really instrument it really well and show the potential of both the printing material as well as the technology of how these type sensing structures can really transform engineering practice.
Cool. Well, I was wondering as well what you think the future holds for this kind of 3D printed steel structure. From what you've seen, I know, I guess this is the company that's doing this part, creating the bridge, but and I suppose it's hard to know until it's it's been deployed and we've done lots of interesting science on the software equivalent, the digital twin. But from what you've seen so far, what do you think the future holds for 3D printing of larger structures or digital twins of larger structures?
So certainly from 3D printing, it's fascinating in that right now it's not cheaper than traditional manufacturing, but we've seen for like plastics and other composite and other materials like that, digital printing has revolutionized design. You can prototype things much more quickly than you could ever before, and it really unlocks a lot of potential in creating new things that we couldn't have done before, both in terms of making them relatively inexpensive to manufacture, but also easy to prototype and refine designs to really make them robust and strong. And I think that really resonates with the engineering side of this, is that the ability to kind of do this quickly and understand in great detail what's going on with the structure will make engineering both more efficient in terms of not costing as much, but also make it safer, because we'll actually have robust data and be able to do iterative approaches and actually have the data confirm that what we're doing is scientifically valid and safe.
Yeah, and to genuinely improve on the traditional approaches to things like bridge construction or other engineering projects. I can imagine that the engineer's toolkit of the future looks something like they have like a augmented reality, cityscape, and then they can put their design on top of that, and then using that, then go and actually design the real thing, thinking about the engineering, and then they'll go and put it in the actual space, and it will fit exactly, that sort of thing.
That's what sci-fi teaches us, like right now. That's what all of the Iron Man makes his suits like that.
Yeah, it looks, the movies make it look easy, but maybe not quite so easy in real life.
Well, and I also think, Ed, you touched on something fascinating there, in that if we do have digital representations of these structures, we can also model things like how people interact with them. I think that's part of the smart city picture, is knowing how people move around. If we change something about our environment, put this fancy new bridge somewhere, is that going to change foot traffic in the area? That's going to impact both the need for how we design these things engineering wise, to layout of cities, to economic effects. More foot traffic might affect local businesses. There's a lot of potential for having robust modeling approaches where we can actually simulate how changing something affects this larger environment, rather than just kind of doing this in isolation and then when we plop it down, hoping that it works and learning painful lessons and expensive lessons if they don't work the way we intended them to.
Well, that leads me to ask an interesting question, which I guess is, historically, thinking of, I guess, bridges in particular, how have we learned those lessons? Have we learned them painfully?
Often we learn them painfully, but as I said earlier, I think there's lessons that we should have learned but haven't, because we don't have any data to tell us that we're doing things wrong.
Right.
Like usually, engineering practice is based on this idea that I take my structure and I think it will withstand a certain range of weight being applied to it. And then there's some reality in which there's a certain range of weights that will in practice be applied to it. Like if there's a football match and right nearby, and tons of local fans get let out of the stadium and go want to drink in the bars, they're going to all cross this bridge. That might, if we know something about, that might be an event that the designer thought of as a potential outlier, but it turns out to be something that's actually experienced with fairly regular occurrences. Then we want to be able to record that and reflect that in our engineering approach, where we actually know that if we say the bridge should respond in this way to this types of loads, and here are the actual loads that have been placed on it, are they overlapping the way that we thought they would? And that's still an open question, because no one's ever recorded continuously all the loads ever applied to a bridge. This will be the first to try and do that.
Well, so as you said, there have been attempts in the past to apply sensors to bridges, but presumably there's more than just the fact of placing more sensors in this case, right? Is there something, because the bridge has been built with this goal in mind, presumably the sensors are built in rather than placed on them?
No, they're actually placed on it. There's a fair amount of engineering work that's gone into designing the system to make sure it's robust. It's going to be out in the weather in Amsterdam. So if it rains or snows, this needs to be weatherproof. So that's another challenge. Another thing that part of the reason this bridge is so heavily spec'd in terms of its sensor density is we'd like to do questions. What kind of questions can you answer with different numbers of sensors? If you only have 3 sensors to put on a bridge, where is the best place to put them? If you have, what scientific questions can you answer with 100 sensors that you couldn't answer with 10 sensors? Are there some pieces of infrastructure where we want to make that investment to put in really dense sensors, and others where we're happy with the information we get from just having a few? I think those are a lot of the questions that having this density of sensors, which doesn't exist anywhere else, can actually answer, and make future efforts to do this more cost-effective as well as robust.
Cool. So Eric, one thing I'm not totally clear on is that there's obviously a big project with our partners in the company. What did you say the name of the company was?
MX3D, yeah.
MX3D, right. So in terms of your personal involvement, what was your role in the project, and how, if at all, did your background in materials science help you with that?
So I've been in charge of a few things within the Turing. So one is I've kind of been a project lead in the sense that there's been a lot of sort of important questions to be answered like getting ethics approval. If we're recording sensor data on real people, we have to go through ethics approval and make sure that we're GDPR compliant. So I was involved in a lot of the discussions on that. Then there's the technical questions of how do we get the data from the bridge into the cloud where we're going to want to run our computations. So that's another area that I've been involved. And our team at the Turing has been working with Autodesk Research to design software systems that are going to allow the researchers to access this data. So those I mostly had kind of a leadership role on that. And the technical side, what I've been doing is writing some of the software that actually implements mathematically what the digital twin is doing. So it's a computational, physics-based model of how to incorporate sensor data with the finite element method. So the finite element method is a common approach that engineers use to solve problems like if you apply loads to structures, how do they bend and deform? But there's surprisingly poor knowledge on how to incorporate known sensor data into those types of models. Usually we do it by trial and error. We say, okay, if I assume that there's this kind of weight on the bridge, I'm going to do a solve of my model. It says the bridge should move like this, compare it with some sensor, sort of look at it, twiddle some knob in an unpredictable way on your simulation and try it again and hope that you cover enough of the possible spaces of what could have happened that you get a reasonable idea of what actually happened. This is actually a much more sophisticated technique where you simultaneously combine the real data with a physics model and say, given the uncertainties involved in everything, so given the uncertainties in my sensor data, given what I know well about my computational model, what I don't know very well about my computational model, and faithfully reflect all those uncertainties, what you'd like it to do is say, here's a really good data point. It's going to tell me exactly what's going on right there. Then there's another sensor some distance away. That's also really good. What happens in between? Classic approach would just be to interpolate, just kind of say, well, it's going to be some smooth transition from one to the other. But there's actually some physics involved in that. We know how materials, given how we displace them in two different places, what they should look like in between. And so this model actually incorporates that in a physically realistic way rather than just kind of fitting some curve between those 2 points, which would be what sort of traditional approaches would try and do in that circumstance.
I guess that those traditional approaches wouldn't be sort of accounting for the subtleties in the material itself or the shape, perhaps.
Yeah, things like that. So a lot of my work, which is based on my background in computational science, is coming up with efficient ways to do this, because these finite element models are often solved on many computer cores, on computing clusters, and to do this model update correctly, you have to solve the model for each sensor point that you have to kind of figure out
What do you mean exactly by solve the model in this case?
So basically, the way these models work is you assume that there is some force applied to the structure, and then you solve the model to determine how it should bend in response to that, the weight that's added to the bridge. And so if you, that you have to specify exactly what that does. And if you have specific points where you've measured that, you'd like to say, if I fix the answer to be exactly what I know the sensor to be, how much does that change what the solution looks like in other places? Right. And so that way you can accurately say how you can account for the uncertainties in all of the pieces of the model. You sort of say, okay, if I know this, what does that tell me about the model? If I know this, what does it tell me about the model? And then add all those up in a mathematically consistent way is what we're doing in this case.
Can you tell us what's the biggest advantage of the fact that this is a 3D printed structure rather than the normally built bridges?
So certainly one thing that the materials researchers have found is that 3D printing works in that you build the material up one layer at a time. So there is sort of a texture to it, and it knows sort of there's different directions that respond differently to forces. So if you pull on it in one direction versus the other, the material actually responds in a very different way. So one potential benefit of this is it seems to be much sturdier in one direction than the other. And so if you have a reasonable engineering understanding of where the structure needs to be strong, you can set up your material so that the strong directions sort of align where you need them most. And if there are certain ways that the structure doesn't react, and bend under real, people standing on it, then you can, take advantage of the fact that this printed steel is stronger in some ways than traditional steel, but weaker in others, and get the benefits of that. So that's one important difference that we've noticed based on the materials tests, is that there's definitely differences between printed steel and traditionally cast steel, and so we'd like to ensure that benefit is actually realized cleverly in the engineering design.
Maybe it's too early to tell, but do you think that there are any disadvantages of printed steel versus traditionally made steel?
For the moment, it's still more expensive to print things.
Right.
I think there's hope that cost will come down, much like it has for plastic printing and other. It's called additive manufacturing. You sort of add up one layer at a time to build something. So that has gotten very inexpensive for plastics, and so I think the hope is that if similar improvements in the cost can be made, then they'd realize some of these benefits.
That being said, I'm imagining some of the slightly dystopian scenarios associated with easily printable steel structures. And I know it's already possible to print like a plastic gun, right? And the schematics are online, so yeah. Maybe perhaps we'll all be printing AK-47s in the shed.
Yeah, that's not scary at all. Or I just like to imagine a gigantic 3D printer just printing buildings and just like around town, just printing stuff. That would be cool.
Mm-hmm.
That sounds like a better scenario. Yeah, definitely.
That's right. We'll move from the London skyline being defined by construction cranes to being defined by robotic arms printing.
Just like these gigantic going. Yeah.
Building up buildings in the city, one floor at a time.
It will be really interesting to see the first major building that's done in this way. I wonder which country will do it first. Probably not the UK.
Here we have it, guys. This is it. Just throwing the challenge out there for all the countries in the world.
If you're listening and you're a budding engineer, then get on it. No, that sounds really cool. Thanks for coming on the podcast, Eric, and telling us all about this really cool bridge project. I've got a couple of other questions I think we have to resolve. So it's not in operation yet, but it should have been, right? So why is the bridge not in Amsterdam yet?
So there's several reasons for that. So first is that it's been very difficult. We're working with the city of Amsterdam to get the permit approving that. That's actually been a surprisingly challenging process. I think partly because of the newness of everything. Like, there were a lot of discussions, like what standard do they want us to provide data on in order to sort of show the safety of the material and the structure. There was a lot of back and forth. We had project calls every few weeks, and it was kind of this cloud hanging over the project. Are we going to get this permit? Are they going to make us reinforce it? And that kind of kills the beauty and the design and the newness of the 3D printed material to have some conventionally constructed reinforcements added to it at the last minute. But the permit has finally been approved. The problem then is in order to get the actual digital monitoring in place, we need to have computer servers there that need a place that they have enough power, where they're sheltered out of the elements. Even if we've ruggedized the sensors on the bridge, there still has to be a sensitive computer server physically located at the bridge. So we needed to get new electrical outlets put in for that. Then the COVID situation slowed down.
Haven't heard of it.
Yeah, that's that's definitely part of this, as well as this is something that's never been done before, and oftentimes you find that when you have something really ambitious, and even when you give yourself several years to kind of get all the pieces together, there are still some challenges that were unanticipated along the way. So we certainly run into a few of those, but the project has progressed, and I think at this point they're hoping to have it in place in the summer. And I think ideally what we'd like is if we can get it in place before kind of lockdowns are eased to the point that people are really out and about in the same way that they were before. A lot of European countries locked down for coronavirus, is we can actually see how the bridge is with and without people using it in different levels, and we can see sort of in real time how this approach can give us more information and more data on how the bridge responds to different environmental conditions, different populations using it, different social occurrences, football matches. It's in the red light district in Amsterdam, so there'll certainly be people out and about at bars and cafes.
Yeah. Well, on that note, you come right to my bonus question, which was you've mentioned it's in the red light district, or it will be in the red light district. What effect, if any, do you expect its positioning there to have relative to if it were positioned across another canal in another part of Amsterdam?
I think partly, it's a very tourist area because of that. So I think that will give the project a bit more visibility. Because of GDPR requirements, we have to put a sign on the bridge telling people that they are being monitored.
Right. They're not being identified in any way, right? It's just their foot, how much they weigh, I guess.
Well, it's so that. Go ahead, B.
Yeah, I was going to say, that's like, you're going to know how much they weigh. You're going to know if they are keeping the social distance, which is now a thing that can be.
Right. Well, could be.
Well, so actually, the fact that we know how much people weigh is actually a very interesting question, because with the small scale version of the bridge that we do have working and monitoring people, the first time that we ever deployed that, we did have on our computer display showing off the sensor readings and how it was detecting people on the bridge. We were displaying people's weight in kilograms, and that actually was a very personal thing to be showing in front of an audience, and people were actually quite reluctant to walk on the bridge because of that. And so when we changed the output, instead of being in kilograms, which is a very personal number to people, to being kilonewtons, which is sort of a bit more removed to people's everyday experience, they just saw that as kind of a cool feature rather than telling something, learning something intrinsic about it. So I think that's an important consideration with these Internet of Things type devices, is that we use it in a way that's constructive for engineering purposes and knowing how structures are used, but don't use it in a way that we're trying to ethically learn things about people like that.
You don't want to cause any existential crisis at people walking past. That would be just
right.
The worst.
Yeah, it certainly would defeat the purpose of monitoring this, to know how the structure is responding and how people are using it, and learning about how this new structure
is going to impact how they use it, right?
Right. Yeah. Exactly.
Yeah. All right, Eric. Right. Thanks very much for coming on the podcast. I think we'll leave it there. Thank you very much.
Okay. Yeah. It's a pleasure to be here. Thanks so much. Enjoyed it.
To learn more about the work going on at the Alan Turing Institute, visit our website at turing.ac.uk. To get in touch with the podcast team if you have any questions or suggestions, email us at podcast@turing.ac.uk.
Music for this episode was provided by Jamin Sun. You can listen to his latest releases at jaminsun.bandcamp.com.
The Turing Podcast is hosted by Ed Cowstry, Tara Callum, Ben Walden, Effie Dennis, and produced by Dan Whitfield for the Alan Turing Institute.